All right, in this module we're going to look at calorimetry calculations, and these are calculations we can do several things with. In general, when we talk about calorimetry calculations, we're talking about taking some kind of an object, a mass of some material, a mass of some object, and dropping it into, most often, some quantity of water. And this object is a hot object, and we know that from the second law of thermodynamics, the lukewarm soup law as I call it, we're all heading down towards lukewarm soup, and the Q, or the heat flow, in this particular device is going to go from the hot object to the cold water. However, that doesn't help us unless we take a look at the thermodynamic system. Let's define the thermodynamic system as being all of the mass under consideration. In other words, we're going to look at both the water and the object together. And if I do that, I'm going to look at heat transfer through that boundary as being zero. If I allow that heat transfer across the boundary to be zero, then I know that there's nothing leaking in, there's nothing leaking out, and the total heat transfer is equal to zero. So if I look at this in the sense of the thermodynamic calculation, if I have the mass of my object times the specific heat capacity of my object times the temperature change of my object plus the mass of my water times the specific heat capacity of my water times the delta T of my water, the whole thing should equal zero. In other words, there's no net heat transfer out of the thermodynamic system. So where does that leave us? Well, how do we get to that point, in fact? Well, let's look at this definition of delta T. Well, delta T is always, in the thermodynamic sense, T2 minus T1. And that's going to be the same thing here, T2 of the water minus T1 of the water. Well, for the hot object, that delta T, the second temperature, is going to be lower than the first temperature, and that's going to be a negative number. For the water, it's colder to start with, and it gets warmer, and so T2 is going to be higher than T1, and that's going to be a positive number. The negative number here and the positive number here are going to allow us to cancel out to a zero net heat flow. So let's see what that looks like in terms of an actual calculation. The first thing we're going to look at, or the common calculation we're going to look at, is if we have an unknown object and we want to find its specific heat capacity. So in this case, we have an unknown object with an initial temperature of 75 degrees C. It's placed in 20 degrees C water. If the mass of the object is 0.735 kilograms, the mass of the water is 1 kilogram, and the water temperature stabilizes at 24.8 degrees C. Find the specific heat capacity of the object. Let's take the specific heat capacity of water as 4.18 kilojoules per kilogram degree K. So let's go back to that basic calculation that we had before. It's the mass of the object times the specific heat capacity of the object times the delta T of the object plus the mass of the water times the specific heat capacity of the water times the delta T of the water is equal to zero. So let's plug in a few numbers and see what this looks like. So this becomes 0.735 kilograms times Cp of the object times, and our delta T in this case is 24.8 minus 75 was our starting temperature. And notice again that's going to be the negative number that we're expecting. And that's going to be degrees K or degrees C. Temperature difference doesn't matter whether we call it Kelvin or Celsius. It's the same temperature difference regardless. And that's plus 4.18 kilojoules per kilogram degree K times the mass, 1 kilogram, times the delta T, which in this case is going to be 24.8 minus 20 equals 0. I kind of mixed these up. I've got the 1 kilogram and the specific heat capacity mixed up, but you can follow that. So let's do some arithmetic here. If we do some arithmetic, we find out that this is 0.735 times minus 50.2, and that's all times CP of the object, plus, and that's going to be 4.18 times 4.8 equals 0. So let's do the rest of the arithmetic. We get a minus 36.897 CP object plus 20.0544 equals 0. Let's rearrange. Minus 36.897 CPO equals minus 20.0544. CP of the object is equal to minus 20.0544 over minus 36.897, and that happens to equal 0.543. And if we follow our units through, this is kilojoules per kilogram degree K, and that in fact is the number for cast iron. So if we look that up in the tables, we'll find that 0.543 is the specific heat capacity for cast iron, and our object then must be cast iron. But we've calculated the specific heat capacity of that. Another common calculation for specific heat capacity is to calculate the final temperature. So I have a 4 kilogram steel forging at 150 degrees C that I drop into a 10 kilograms of cooling oil at 20 degrees C. If the specific heat capacity of the steel and the oil are 0.494 kilojoules per kilogram degree K and 1.7 kilojoules per kilogram degree K respectively, what is the final temperature of the oil? So once again, let's just do this. The mass of the forging times the specific heat capacity of the forging times the delta T of the forging plus the mass of the oil times the specific heat capacity of the oil times delta T of the oil has to be equal to 0. So let's plug some numbers in here and let's see how this looks. All right, so the mass of the forging is 4. The specific heat capacity is 0.494. My delta T, I'm just going to plug this in as T2 minus T1 for a minute. I'm just going to call that of the forging, plus the mass of the oil, which is 10 kilograms, times the specific heat capacity of the oil, which is 1.7 kilojoules per kilogram, and times delta T, which is T2 minus T1, and I'm going to call that of the oil. Now the most important thing to recognize when we're doing this calculation, because right now it looks like we don't know any of the temperatures, but we do actually know the initial temperature of the forging and the initial temperature of the oil. But what we have to remember is that the final temperature of the forging and the oil is the same. In any calorimetry calculation, when we get the final temperature of the 2 or 3 objects that are mixed together, the final temperature is always the same. So that allows us to do a little bit of algebra here and solve for the unknown. So I'm going to take the, let's just fill in those temperatures now. So that becomes 1.976 times T2 minus 150 plus 17 times T2 minus, we started out at 20, equals 0. And we know that that's going to be a negative number, and that's going to be a positive number, and we're perfectly fine with that. So let's now multiply this out. So 1.976 T2 minus 296.4 plus 17 T2 minus 340 equals 0. All right, let's bring both of these two across. 1.976 T2 plus 17 T2 equals 296.4 plus 340. I get, if I combine these two together, I get 18.976 T2 equals 636.4, or T2 is equal to 636.4 divided by 18.976, or T2 is equal to 33.6 degrees C. So I know my final temperature of the oil in the forging are 33.6 degrees C. That's two simple calorimetry calculations that you can do.